Momentum is a fundamental concept in physics, representing the quantity of motion an object possesses. Mathematically, it is defined as the product of an object's mass and its velocity. The equation is simple. Momentum, P, equals mass, m, times velocity, v, or P, E, mv. This relationship highlights that momentum is not just about how fast something is moving, but also about how much stuff is moving. The more massive an object is, or the faster it moves, the greater its momentum. Now, let's dive into the concept of force and how it relates to momentum. According to Newton's second law of motion, the relationship between force and momentum is crucial. When a force is applied to an object, it causes a change in momentum over time. This change can be quantified by the equation force, F, equals the change in momentum, dP, divided by the change in time, dt. This can be expressed as F equals dP dt. What this means is that the greater the force applied to an object, the greater the change in momentum will be, and the faster that change will occur. Think of it this way. If you gently push a stationary soccer ball, it will roll slowly, gaining a small amount of momentum. However, if you kick that same soccer ball with all your might, the change in momentum is much more significant and happens almost instantaneously. The larger force creates a more substantial acceleration, propelling the ball at a higher velocity and thus giving it a greater momentum. This principle of momentum change is essential in understanding the conservation of momentum. The law of conservation of momentum states that in a closed system, where no external forces are acting, the total momentum before an event must equal the total momentum after the event. This principle allows us to solve problems involving collisions and interactions between objects. For instance, in a perfectly elastic collision, where no kinetic energy is lost, we can use the conservation of momentum to calculate the final velocities of the objects involved. By setting the total momentum before the collision equal to the total momentum after, we can derive equations that help us find unknown masses or velocities. Let's consider a practical example. Two ice skaters pushing off from each other. Before they push off, their combined momentum is 0. After they push away from each other, their individual momentum must still sum to 0. If one skater has a mass of 50 kilograms and moves away at a speed of 2 ms, we can calculate the velocity of the second skater, who has a mass of 70 kilograms. The momentum of the first skater is 50 kilograms multiplied by 2 ms, which equals 100 kilograms. To conserve momentum, the second skater must have a momentum of 100 kilograms, opposite direction. Therefore, if we set up the equations 70 kilograms v equals to 100 kilograms, we can solve for v, revealing the second skater's velocity. Understanding how forces cause changes in momentum is not just theoretical. It has practical applications in various fields, from engineering to sports to safety design. For instance, car manufacturers use these principles to design crumple zones that absorb impact forces in collisions, reducing the change in momentum experienced by passengers and enhancing safety. In summary, momentum is a vital concept that describes the motion of objects, and forces play a crucial role in changing that momentum. Larger forces lead to quicker changes in momentum, and the conservation of momentum provides a powerful tool for calculating unknowns in dynamic systems. By grasping these principles, we gain insight into the mechanics of the world around us, allowing us to predict and understand the behavior of moving objects in a variety of contexts.